detecting a spacecraft at a distance of 0.9 light years, approximately 8.5 trillion kilometers, with the James Webb Space Telescope, JWST, presents significant challenges due to the vast distances and the telescope's sensitivity limits. To determine how large a spacecraft would need to be for JWST to detect it, we need to consider several factors. 1. Infrared emission of the spacecraft. 2. JWST's sensitivity limits. 3. Distance attenuation of the signal. 4. Size and temperature of the spacecraft. 1. Infrared emission of the spacecraft. Assuming the spacecraft is a definite emitter of detectable infrared IR radiation, its detectability depends on temperature, T. Higher temperatures increase IR emission. Surface area, A. Larger emitting areas produce more total IR radiation. Emissivity, how efficiently the spacecraft emits IR radiation, assuming eta 1 for a blackbody. The total power emitted per unit area by a blackbody is given by the Stefan-Boltzmann law, PA equals sigma T4, where minus PA is the power per unit area, W squared. Sigma is the Stefan-Boltzmann constant, 5.67 times 10 to the minus text WF minus 2, kx minus 4. 2. JWST's sensitivity limits. JWST's detection capabilities in the mid-infrared, mid-IR range are characterized by its sensitivity to faint sources. Sensitivity limit at 10 millimeters, approximately 0.1 mutex JY, microjanskis in a 10,000 second exposure. Flux density conversion, 1 mutex JY equals 10 minus 29 text W minus 2, Hertz minus 1. Measure 3. Distance attenuation of the signal. The flux received by JWST decreases with the square of the distance. F equals frac P4 pi d squared, where F is the flux received, W meter squared. P is the total power emitted W. D is the distance to the spacecraft M. Step 4. Calculating the required size and temperature. Step 1. Calculate the required flux. The minimum detectable flux F of tex min at 10 millimeters is F of tex min equals 0.1, mu tex y equals 1 times 10 to the text Wm squared Hertz minus 1. However, since we're dealing with power per unit area per unit wavelength, unit lambda, we need to convert this to text W m squared minus 2 m minus 1. F lambda equals frac F tex min C, that lambda equals 10, like Ken, frac 110, 1 times 10 to 30, m squared minus 2, text 1 times 3 times 10 to the 8, text m for sen. 10 times 10 to the minus 6, x text with approx 3 times 10 to the 14 text w mentenet, mu text m squared minus 1. Step 2, determine the spacecraft's emission. Using Planck's law, the spectral radiance m lambda t of the spacecraft is m lambda t equals frac 2 pi hc squared lambda phi left frac 1 e lambda kt minus 1. For a spacecraft at temperature T, we calculate m lambda t at lambda equals 10 mu text m. Step 3. Calculate the required emitting area. The flux received at JWST is F lambda equal frac lambda t times A 4 pi d squared. Solving for the emitting area A equal frac times 4 pi d squared m lambda t. Example calculations. Scenario 1, spacecraft at 300K, temperature T, 300K, approximately 31.4 Wm minus 2 mu tex squared minus 1. Required area A equal frac 3 times 10 squared minus 42 mu text m squared minus 1 times 4 pi 8.5 times 1031.4 text Wm squared minus 1 approx 8.7 times 10 squared 20 squared 2. Equivalent radius r approx 5.3 text astronomical units AU. Scenario 2, spacecraft at 3000K, temperature T, 3000K, and lambda T approximately 76,400 text, mu text m squared minus 1. Required area A approx 3.6 times 10 to the 22, equivalent radius r approx 0.0434 AU, about 5 million kilometers. Scenario 3, spacecraft at 10,000K, temperature T 10,000K, m lambda T approximately 259,500 text Wm squared minus 1. Required area A approx 1.05 times 1020 text N2. Equivalent radius r approx 0.006 text AU about 900,000 kilometers. Conclusion. To be detectable by JWST at a distance of 0.9 light years, a spacecraft would need to be exceptionally large. Even at extremely high temperatures, 10,000 K, the required emitting area is comparable to the size of a star. Extremely luminous and infrared, the spacecraft would need to emit tens to hundreds of gigawatts of power in the infrared spectrum, impractically hot or large for current technology. Such a spacecraft exceeds any reasonable size or power output achievable with current or near future technology. Alternative detection methods. Given these impractical requirements, detecting a spacecraft at such a distance might be more feasible through active emissions. If the spacecraft uses powerful lasers or radio transmitters directed toward Earth, transits or occultations, observing the dimming of background stars as the spacecraft passes in front. Gravitational effects, detecting perturbations in the motion of nearby objects due to the spacecraft's mass, unlikely for small masses. Summary, size required, a spacecraft would need an emitting area of at least 10 to the 19 to 1023 text m², depending on temperature. Emission requirements, total infrared luminosity on the order of 10 to 10 to 1014 watts. JWST limitations. JWST is not designed to detect such small and faint objects at interstellar distances. Therefore, unless the spacecraft is extraordinarily large or emits extremely high levels of infrared radiation, it would not be detectable by JWST at a distance of 0.9 light years.